Cool. They have lack of focus here. All right. Yeah. So let's talk about get num and get denom. So the idea is you'd like your numerator and denominator to be private. Right? Why is that? Because suppose that you're handling division by 0 in a particular way. Suppose you have a flag that you're setting in your class, and whenever you construct a fraction or do an operation which results in a denominator of 0, you set a flag, right? To say, hey, this number is not a number, and then you just look at that flag before you do other operations or print or so on and so forth, right? Well, if a main program can come in and just say, you know, fraction dot denominator equals 0, your flag is not going to get set, right? So there's good reason why you would probably want control over, you know, changing the value of the denominator. So you make it private, right? And now the only way that a denominator gets set is by your code, right? Not by outside code. But if somebody outside wanted to know what the numerator or denominator of the fraction was, right, they wouldn't be able to just say fraction dot numerator because it's private. So you make these accessors like get num and get denom, and you make those accessors, those methods, public, so somebody can say, you know, fraction dot get numerator, and they'll see what the numerator is. They can read these now, but they can't write them, so you control the access to these fields. Now, why do you want to do that? Let's see, something else I was going to say about that. Oh, so you can use these in your fraction code, right? To add a fraction, you want to add, you know, you need to get the numerator and denominator of the incoming fraction, right? You can't just say, you know, take the arguments numerator and denominator by dot num. You have to use these methods also, right? So you can use those inside your methods, and it just gives you controlled access. So this is a standard thing to do. Now, if you wanted to allow outside code to modify these things, you could make mutators, set num and set denom, but you could do those on your terms. In other words, in the set denom, you could say if the argument is 0, then I'll go ahead and set my internal flag to say this is not a number, and so on. So to test them, just make a fraction, 2/3, and then just, you know, print the return value from fraction.getNum, fraction.getDenom, and you should see a 2 and a 3 respectively. All right. I don't have Spotify, but my fiance and I swap CD mixes with each other, and that's usually what I'm listening to in the morning. She has much more diverse taste in music than I do. But it's been an excuse for me to go out and like really think about like what are some of the really cool songs I like that I don't listen to much. So I pull out some oldies. My taste is actually a lot of different stuff, but I kind of grew up on, you know, rock and a lot of Pink Floyd was always my favorite band. Especially their stuff from like, you know, the 60s. Fish is cool. Very cool. All right, let's see. Yep, that's all there is to an accessor. Just return. You don't even need x dot numerator, right? If you're writing a method inside a class, and that class, you know, defines a field called num, here we'll do it right here, integer get num. Just return num. That's all it takes. right, so pretty straightforward. Yeah, it does seem too easy, but that kind of happens in Java. Um, Sometimes these things seem really straightforward. As long as it's happening within the fraction class, it can still read, modify the numerator and denominator fraction passes as an argument. I don't believe. Maybe it can. Yeah, try it. If it doesn't work, use the accessor mutator. But mark these things private anyway, so that outside main program and such can access them using those.
Hey, Nick.
Yeah.
Can you go over, okay, so like in C, right, when you have multiple files that you need to run in the same program, you have to like run them, you use a make file or run them on the command line, right? How does that work for like say if I want to test my class in a test file, like, is it the same way or how does that work?
So in Java, if you have several classes and they're defined in several files, right? Each one that you compile creates a new .class file from the .java file. But if you need to use a class, right, the tools will look in your current directory for the appropriate class file. So as long as you're working in one directory, you can have 5 or 6 .java files compiled to 5 or 6 .class files, and they can use each other, and they'll find each other because they're in the current directory. If you get fancier, if you start making libraries of classes that you're going to put somewhere other than your current directory, and then you want to start looking at what's called the class path. That lets you specify, look in this directory for classes. And if that's not fancy enough, then you can start making jar files, which are basically like tar files. They're collections of classes that go into a single file, and you can say, hey, look in this jar file for any classes that you haven't found elsewhere. And that's analogous to like a runtime library in C. And compiling a make file, can just do Java C on all the pieces. And you can do anything in a make file you want. It doesn't have to compile C. It doesn't have to compile anything. But you could build one the same way, right? Make your target whatever your main program .class is, and then list the pieces, the dependencies, and so on. But usually when you compile the main program, if it needs classes and the source code for those classes is in the current directory, they get compiled automatically too. Let's see, using getNum and getDenom from our main program, sure. So something like fraction f equals new fraction 1 comma 7, and then you could say integer n equals f dot get numerator. Right, so f is a fraction, it's an object of type fraction has a getNum method, so this is calling the getNum method in that fraction, which should return the numerator of f, which should be 1. And then I can print out n or whatever. Cool, you're welcome. Let's see, so does private only block code that is not in the same class? Yeah. So private basically blocks everything outside of the current class. And public grants access to everything. There's a package level in between that we're not going to talk about yet. All right, so Thursday I've decided, at least for this week, I'm going to use class time for kind of an open lab. Because last week I noticed when we were going through some of these ideas, people were writing code and trying it and having syntax errors and helping each other with it and so on and so forth. And I want that to happen, right? but I would rather that was happening at a time when, you know, you could ask questions and screen share and things like that, instead of just, I tried typing in the code I saw and it didn't work. I guess, you know, I'm done. So we're gonna try it this week, right? Thursday, basically, usual meeting time, 10 o'clock to 10:50. But I'm not going to plan a lecture. Okay. If you don't feel like you want to come and hang out and work on code, that's fine, right? I don't take attendance. But if you want to, you know, work on code, if you've got nagging problems with PA1, if you want to go through sample code or whatever, right? We can hang out in class time and do that. And this is not just for PA1. This can be, you know, for general Java stuff. It can be for PA2 if you're looking ahead, and so on and so forth. So it's totally up to you whether you think that's something that that will benefit you or not. I won't lecture with a prepared lecture, and I won't, you know, start anything that we'll be building on that you would, you know, be missing out. But, you know, if someone says, can we go through an example of such and such, I might put up some code and have people make changes to it and so on. So yeah, that's going to be this Thursday, and we'll see if it becomes a regular thing or not. We'll do whatever makes the most sense. Is there a requirement on where we call our reduce function? No, but be aware of, you know, the fact that there are mean people out there in the world who might do something like, you know, a equals 2 over 1, b equals 1 over 2, for I equals 1 to 100,000, p equals p times a times b, right? And if you do this, right, I have a running product that's 1, I multiply by 2 and multiply by half. P is always going to be 1. But if you don't reduce after you multiply, this is going to blow up really quickly, because your numerator is going to get to be, you know, 2 to the 1,000th, and your denominator will be 2 to the 1,000th. And that's going to blow up, you know, your ability to handle these as integers. So you would like to reduce any time that you have a fraction to avoid, you know, if someone were to happen to run a test like this, to avoid having your code crash. So reduce when you multiply, when you divide, when you add, when you subtract, when you construct. If you reduce when you construct, you don't have to worry about those others. If you construct to get the return value from, say, multiply, add, subtract, divide. But if the only time you call it is in toString, then this will get you into trouble. So keep it reduced. But if you can call reduce in toString, right, just move that to your constructor, and then life is good. Oh, you've missed making programs from multiple pieces, and some details on PA1, and the fact that Thursday is an open lab, and it's all recorded on the video, so you can catch details from there. Yeah, catch the video. You only missed 14 minutes. All right. Let me just touch base. What kind of comments you want before each method? Oh, you know, name of the function, what the arguments are, what the return value is, what it does. Right? Doesn't have to be fancy at this point. We'll make it fancy later, but you know, right before your add method, you know, add 2 fractions, the argument is the number you want to add, the return value is a fraction. If you normalize it, you know, that would be a good place to mention the return value is normalized. If you don't normalize it, definitely that's a good place to mention the return value is not normalized, right? So somebody knows, you know, do I have to normalize this and so on. And your divide function, right, what happens if you divide by 0, right? Division by 0, you know, sets a flag, or division by 0 changes the fraction to this form. So just basic information. And we'll formalize that later on in the quarter. But for now, just, as they say, just the facts. So when we make a main program, we declare it as public static void main, right? So let's talk about what this static business is about. Remember, the idea from yesterday is that if you have a static method inside some class, you know, a class called ha, and it has a static function, I don't need an instance of that class to call my function. I can just say class name dot method name, right? This is what happens when you say Java my main class. Right, so suppose you write a file called myMainClass.java, and inside that file you say public static void main, right? When you say Java myMainClass, what happens is the JVM tries to execute the following static method: class name dot main, and it calls it with a single argument, which is an array of strings. Right? That's just how Java is set up, so that when you ask to run a program, that's how it executes it. It executes it as a static method in that class. So if we make a main method and we don't make it static, that's totally legal. But when we try to run our program by saying Java main in this case, it's not going to find it. And similarly, if we don't give it an argument that's exactly one array of strings, it will say I don't know, where the main program is. Can you still use an instance of the class on a static method? So if your question is, suppose I make an instance of ha, can I say that instance name dot fun? And it turns out you can, but you're not supposed to. And you get some kind of warning about it, depending on whether you turn on warning messages through lint. But you can do it, but you're not supposed to. And there's probably something slightly off in the organization of the code if you feel like that's something that needs to be done. What would a cannot find symbol error mean? Totally depends on the context. But it's probably a typo or something that's scoped differently, like you're looking for a variable and it's not actually a part of the class, or you don't have access to it. All right, so that's the whole business with the static word in public static void main. And again, the only time you're going to have to use static for now is really in public static void main. If you're calling methods inside here, inside your main class, or if you're setting up, fields in here, variables and so on, and trying to get to those, you may find that they need to be static. But in general, if you start getting messages from the compiler about, can't make static reference from non-static context or vice versa, don't just start throwing in the word static to try to fix it, okay? You'll find lots of recommendations online about, just add the word static, but don't do it, okay? You're going down a rabbit hole that you don't want to go down. Are we really? Eight cameras, awesome. Cool. Very nice, thank you, people. I need to find a way to be able to display these while I'm screen sharing. Cool, excellent. Yeah, totally. All right, cool. So let's make some classes. Chancellor Palpatine would have been more impressive if his name didn't sound like a shampoo from the 80s. All right, yeah, do. All right, let's make a linked list class by hand, okay? And we're not going to do this for PA2. For PA2, you get to use the built-in linked list library, okay? Yeah, Darth Sidious or Pantene. All right, we're going to use built-in classes for linked lists and hash maps and things like that. But let's just go through as another example of making a class and putting pieces together and multiple files and all that. Let's just do a linked list class. Okay, we know about linked lists from 222. We coded them up in C. Let's just code them up in Java. And the mechanics of the code will probably feel somewhat familiar, but I think you'll find the implementation in Java is a little nicer. So let's start off with our main program. I'm going to make a my list. I'm going to call it LL. And I'm just going to add some numbers to it. And then I'm going to print out the contents of the linked list. So that's our whole main program we're going to use to test this class that we're developing. All right, so we'll make a linked list called LL, and then we'll call the add method that we're going to write to add a few numbers to this list, and then we'll go ahead and print it out. And this is going to be a simplified version of linked list. I'm just going to add by inserting right in the beginning, so I don't have to do all the annoying stuff that I made you do. So let's make a mylist.java. If I don't put comments in, then I'm a hypocrite. So there's my comments. So what do we need in a linked list? We need a Sentinel node, right? Because I'm doing linked list with Sentinel nodes. So what is a Sentinel node? Well, it's going to be some kind of node. All right. So we'll start off with a Sentinel, and we'll construct it. Well, maybe we won't construct it there. We'll start out with a new Sentinel node. Okay, so we're going to need a node class, right? So let's go ahead and make that. So here's our single node. So what does a node have? It has data. We'll stick with integers. And then what should the next field be? What type of thing is this pointer to another node going to be? What can I put in here? Yep. It's just node next. And that can feel a little weird, right? Because we're putting a node inside a node. It's okay. Java will handle it. We could put all of these in the same file, and you get different class files on the output side, and they have like $signs and numbers in them and stuff. But I think it's cleanest to put each class in its own file. It's nice practice. So yeah, this is recursion in a strange way. Okay, so that's really all we need for a node: piece of data and a next field. But let's do some other stuff. Let's make a constructor. Let's make a constructor. Alright, there's a constructor that takes an integer argument and it creates a node, sets the data field to the argument, sets the next field to null. Oh, we'll do a lot of recursion in Java too. But it's good stuff. Alright, that's probably all we need for our node class. We could put in, you know, a two-string method. We could do all kinds of stuff, but for now we're just gonna keep this simple. So we got two fields in a node, a data field and a next field, and I'm putting in a constructor. And I'm just gonna leave everything public. I'm not gonna bother with accessors and mutators and so on. All right, so our linked list, we need a sentinel node. Let's make a constructor. So how do we construct? Well, we sent sentinel equal to new node. And, you know, I'll just give it some bogus value. This will construct a node. It'll set the data value to 42, but more importantly, it will set the next field to be null, and I'll set sentinel equal to that node. That gives me an empty linked list, a list containing just a sentinel that points to null, which tells me there's nothing else in here. Yes, absolutely. That's the key to recursion. If you believe it'll work, it'll work. All right. So let's write these add methods and print methods. All right. So add is going to say let's add an integer to our list. So we have to make a new node. So node temp equals new node, and we can pass the data field to that. And then how are we going to insert this? Well, quick refresher on linked lists. So the sentinel is pointing here already. We're going to make this new node temp. And we want to change temp to point to here, and then change the sentinel to point to temp, because I'm inserting in the beginning. All right. So first thing, temp should point to whatever sentinel is pointing to. So I'm just going to say temp dot next equals sentinel dot next, and sentinel next equals temp. There's our add method. All right, make a new node, have it point wherever the sentinel is pointing, have the sentinel point to the new node. All right, and let's finally add our print method. So it doesn't need any arguments. So we'll start off with the thing the sentinel points to. And as long as that's not null, we'll print out the data field of temp. We'll move to the next field, and that's our print method. So there's our linked list class, and it's, you know, about as straightforward as I think you could hope. Right? The print method in particular is like, it just does what we want it to do and nothing else, right? Make a temporary node to point to whatever the sentinel is pointing to, and as long as that's not null, print out its data value and move to what that points to. Alright, so we should be all set here. How many errors are we going to get? So I've got my 3 Java files. Let's compile main. Right, so now I've got 3 Java files and 3 class files. Wow, no errors. That's impressive. All right, so let's run it. And there's our data in reverse order of how we inserted it. Right, so that's you know, yeah, we already know linked lists and we've done this before in C, but still it's a fair bit easier in Java. There's no mallocs, there's no arrows, there's no stars. You know, it kind of flows more naturally, at least to me it feels like, from my brain to the code. And we could make a make file, but we don't really need to. But let's see what happens. Let's change this method. Let's print this stuff out on one line. So what happens if I just recompile my main program? Looks like it recompiled my linked list class. All right, that bothers me that the makefile is unnecessary. Yeah, you can make a makefile though. I mean, that's totally legal. And you know, when I'm doing stuff, I usually just javac star.java because I don't want to think about it. But yeah, let's see. What was this question that I missed apparently? Javac main compiles all files. Yeah, it does. So definitely, if the class files don't exist, Javac main compiles those other .java files. But it looks like, and I didn't actually realize this till just now, it looks like, you know, even if I change a Java file, if I recompile main, it recompiles that changed Java file. So that's kind of cool. Yeah, kind of like built-in makefiles, which, you know, sort of usually makes me kind of suspicious, because, you know, I like knowing exactly what's going to happen when, but it seems to work. All right. So other questions about that? Are we going to need makefiles while using Java? If you start putting things in different directories, then yeah, you probably want to do a makefile. If everything is sitting in one directory, like I said for PA1, if I can just say javac and you know, fraction.java, and that'll compile everything that needs to be compiled, then you don't need a makefile. And the easiest thing is, you know, if you don't submit class files, then compiling the main program should compile everything, or the main fraction class should compile everything. All right, so there's sample code on the server for that. The C in javac stands for compile, at least in my mind. Jar files work just like tar files, so you can say jar cvf ll.jar *class. And now you've got an ll.jar, and it's got all the class files in it. And you can do a tvf to see what's contained in there. There's a whole lot more you can do with jar files, though. And you can put in entire directories and packages and so on. You can also make runnable jar files, so that, for example, if it's sitting on your desktop as an icon, you can just click on it and it runs your main program automatically. All right. So that's the an example of making a sort of more complex class with more parts and pieces to it. But there's a linked list class built into Java. And this is what we're going to actually use. So class linked list, and we're going to dig a little more into this documentation now, right? And we're going to have to talk about this in a minute. This is something called a generic. But a linked list is actually a particular type of what's called an abstract sequential list, which is a particular type of what's called an abstract list, which is a particular type of something called an abstract collection, which is a particular type of something called an object. So there's a hierarchy of classes. And rather than, totally reinvent the wheel when somebody was creating this linked list class, they started with something that's called an abstract sequential list. And we can, look at documentation for this and see what an abstract sequential list is. And it's got, ways to add things and ways to remove things and so on and so forth. And on top of that class, somebody created the linked list class. When we, write a class for playing 20 questions, we're going to put it on top of other classes that already exist. When we make a tic-tac-toe board, it's going to be made on top of a class that makes a box, right? So yeah, inheritance is a key word here. We have the ability to not have to go back and reinvent the wheel, but to start with a class that already exists, add things to it, change things that are already in there, and tailor it to our own purposes. We might do a tic-tac-toe game. We might do something different. I want to do something that we can network. Could do chess. That's going to be a little more work on the GUI side. Ooh, you made one in Python. Cool. We could do Battleship. We'll figure something out. All right, so this tells you a little about this, right? Doubly linked list implementation of list and DQ interfaces, whatever that might mean. This implementation is not synchronized. We're going to talk about threading towards the end of the quarter. The fact that you can write code in Java that has multiple threads running at the same time. And one of the issues when you do that is being able to share memory and making sure that two things that are sharing the same section of memory don't interfere with each other. Well, we could make RISC. That would be cool. So yeah, so for example, if you have different cores on your machine, multiple cores, you could have threads running truly in parallel that are, both executing in their own context. Even if you only have a single core machine, though, it may be useful to think of your system as being able to run multiple things at once, right? That's what we do on PCs. So for example, if you're writing a word processor program, you're typing. After you go a certain amount of time, you want to automatically save what the person has typed. Well, if it takes, 5 seconds to do that, you don't want the screen to freeze for 5 seconds while this file is being saved. So you would typically start that in another process or another thread that would start, writing out to disk and so on and so forth, but you're still typing and you see your screen updating and so on. That may be happening on multiple cores, could be happening on just one CPU, one core. But that's okay. You have 16 cores. Wow, that's awesome. I could use those. Poker, Go Fish, Monopoly. We could do any of those. Go Fish is an awesome game. And Crazy Eights. So we'll talk about synchronization of threads, but for example, in the word processor example, suppose that while you're typing, you move a paragraph of text from the beginning of your document to the end. Well, if you're not careful and you're simultaneously saving this file, right, you might start reading the file from the beginning and you see that paragraph in the beginning, and now that file gets moved to the end, and as you continue reading it, now you've got another copy of that paragraph at the end, and the file you just saved on disk is gibberish, right? It's got 2 copies of this paragraph now, right? So you'd like to make sure that there's synchronization. So most of these classes will talk about whether or not it's safe to use this in multiple threads. So constructors, we can construct an empty linked list. Okay, that's the same constructor we just wrote. And then there's an add method, which adds an element to the end of the list. There's an add first method, which adds to the beginning of the list. There's clear to get rid of everything. And there's a whole lot more methods in here than we made, and a whole lot more methods than we used in 222. But these are all the different things you might want to do with a linked list, right? Add to the beginning or the end, clear things out, make a copy of it. See what the first element of the list is, but don't remove it, right? This is like a peek function for a queue. Get an element at some particular position. So treat this list like an array and give me the 5th element, right? Find the location of an element in the list, you know, or tell me if it's not contained in there. So that's a search function, but also a way to say, you know, yeah, this thing is in the list and it's at position 7, and then you can say get, you know, the element at position 7. And so on and so forth. And this is a really high power class, right? It lets you do a lot of things with linked lists beyond just, you know, insert, remove, search, print. And it lets you convert it to an array and all kinds of useful things. There's also this notion of an iterator, and we touched on this a little bit in 222. This idea that, you know, how do you go through the elements of a data structure? If it's a linked list, you can just start from beginning and go to end. If it's a hash, there is no first element, there is no last element, there is no nth element. So we need some way to go through the contents of a data structure, and this is going to use something called an iterator. We'll talk about details of that later. Yeah, I missed something in chat because now we're like hacking the world, which is like Go Fish ++. Okay, yeah, that's a logical path to hacking. All right. So observation. Our main program here, right? We created a linked list and we added, you know, a bunch of numbers to it, a bunch of integers, right? Do we know that these are integers, or are they doubles, or are they floats? Well, there's no periods at the end and they're all whole numbers, so they could be integers, but they could be doubles or floats, right? But suppose we wanted a linked list of strings. Suppose we wanted to store a bunch of names in our linked list and print those out. Right? What would we have to change in our linked list implementation to make a linked list of strings? Obviously, when we add things, we have to pass a string instead of an integer. That's pretty clear. What does our list code look like? Well, when I construct a sentinel, I might want to, you know, put something in other than a number, right? To add something, my integer is going to become a string. Constructing my new node is the same. Getting the next node is the same. Moving to the next node is the same. The print method is exactly the same. I can print out with print line, right? Nothing else changes in here. Really, all that changed was, you know, the thing I passed to the Sentinel when I constructed it, and the type of variable that I want in my add method. But none of the gory logic changed, right? And in my node class, this changes to a string. This changes to a string. That's it. Right? I've got a linked list class now for working with strings. And I changed, you know, 3 or 4 places where the word int appeared. I changed that to the word string, and I got a linked list for strings now.
The linked list can only take one data type, I assume.
The way that we just wrote this one, yeah.
Right.
But, it's a good question. Right, what if we wanted a linked list that could store, you know, a string and an int and a double? Could we do that? Right, really all we need to do is in our node class, instead of saying our data is a string or an int, we could make it a object of type, you know, cool node or cool data, and have that thing be a class that contains an int and a string and a double. Right? This can be pretty much any type of object that we want. And we just have to change this and a few other places from string to that type of object. We could make this a my list, and each node could contain a linked list. And all we'd have to do is change this to my list, change this to my list, change this to my list, and so on and so forth. So what we're going to see is that there's a lot of times when we define a class to implement some sort of data structure like a linked list, and if we write this to implement a list of integers or strings or characters or doubles, the code is almost exactly the same. Really, the only thing that changes is the type of object that we pass to some of our methods. And so Java has this concept of what's called a generic, right? Or generics if you can't type. A generic basically lets us say when we construct a linked list from this class, we're going to tell it what kind of objects we want to put in our linked list. And we can just say linked list angle bracket string, linked list angle bracket integer, linked list angle bracket double. And it will be the same code underneath, it'll be the same interface, but it'll work with different types of objects. All right, so we'll continue from that tomorrow, and we'll go through some specific examples. Later on in the course, we'll see how to write our own generic classes as well, but we'll worry tomorrow about how to use generics with linked lists and other classes like that. All right, we're out of time. Have a good one. I will see you next time.